Hello everyone, and welcome to the Forestry Adaptation Community of Practice webinar today. For those of you who don't know me, my name is Annette Morand, and I'm the facilitator of the online adaptation communities of practice. And those are run by us here at OPR, which is the Ontario Centre for Climate Impacts and Adaptation Resources, and we're located at Laurentian University in Sudbury, Ontario. So the way the webinar will run is as follows. So after this very short introduction, we're going to have the main presentation, which will go for about 40 minutes or so. And then at the end of the webinar, we're going to have some time left for any questions that you might have for Mike. So if you have any questions during the webinar, we just ask that you please hold them until. And before we get going, just a few housekeeping items to go over. So first, for those of you who dialed into the conference call line, your lines have been automatically muted. And the reason for this is just to avoid any audio distractions or feedback during the webinar. But you can ask a question during the Q&A session. And all you'll have to do is dial *6, and that will unmute your line. But please do keep your lines muted during the presentation. Also, you're going to notice there's a chat box on the left-hand side of your screen. So this is where you can field your questions that you might have during the Q&A session. As well, if you have any technical difficulties during the webinar, you can actually click on my name and you can send me a private message and I can try to help you as best as I can. I also want to mention that we are recording the webinar today, and I'll be sending out a copy of the recording to everyone who pre-registered with me, and we'll also be posting it to the Community of Practice website. And finally, I know we have some people on the line who may not be familiar with what the Forestry Adaptation Community of Practice, or the FACoP, is. So I wanted to quickly mention that it's an interactive online community, and it's dedicated to those who are working in forestry or just simply interested in forestry and climate change adaptation in Canada. So it includes features such as an online resource library, news articles, discussion forums, and more. And it's free to join. So if there's anybody on the line today who's interested in learning more about the FACoP, the link is in the chat box there. So with that, we are very excited to have Mike Flannigan on the line with us today to talk about the future of wildfire in Canada. And just so you know a little bit more about your presenter, Mike is a professor of wildland fire with the Department of Renewable Resources at the University of Alberta. He's also the director of the Canadian Partnership for Wildland Fire Science, which is a three-way partnership with Alberta Agriculture and Forestry, Natural Resources Canada, and the University of Alberta. Mike has a bachelor's degree in physics from the University of Manitoba, a master's degree in atmospheric science from Colorado State University, and a PhD in plant sciences from Cambridge University. His primary research interests include fire and weather and climate interactions, including the potential impact of climatic change, lightning-ignited forest fires, and landscape fire modeling. Mike's been studying fire for over 35 years and has published over 200 papers. He is the editor-in-chief of the International Journal of Wildland Fire from 2002 to 2008, and has taken on leadership roles with the U.S. National Assessment on Global Change, IGBP Fire Fast Track Initiative, and Global Change Terrestrial Ecosystem efforts on the global impacts of fire. So on behalf of everyone joining us, I'd like to extend a very warm welcome to you, Mike, for taking the time to present this webinar for us today. It's very much appreciated. So without further ado, I'll now hand things over to you.
Thanks, Annette. Great to be here. And so I'm going to talk about the future of wildfire in Canada. And I don't have a crystal ball, so no one knows what the future will bring. But based on what we have learned, we can make some guesses about what the future may be like. So this picture is from British Columbia. It's just south of Ashcroft, BC, and it's July 14th at 4:45 p.m. and it's a Friday, and it is hot, dry, and windy. And you'll hear this phrase a few times: hot, dry, and windy. It's about 36 Celsius. The winds were 25, gusting 45. RH was 12 to 13%, and you can see that massive column in the background. We were here. We actually drove a little further along the highway. We're closer to this fire over here, just south of Cache Creek, for about 4 hours. And that time, that smoke from this cloud reached Jasper National Park. So It was really burning. You could see flames flaring up quite visibly. Perhaps 100 meters or so. It's hard to tell with the height of the trees. So this was an indication of what was going on in BC. The previous Fridays, when all the fires, over 140 fire starts, many near communities, and it was a very active season. Is this indication of what's to come? Maybe. So, today I'm going to talk about fire in Canada, a little bit about globally, talk about climate change, fire and climate change, and what options do we have. And that's a picture from about 10 years ago or so. The red spots are hot spots from a satellite, fires in Quebec, and this band of gray, yellow stuff is smoke that smoked out the eastern seaboard. So, on average, we burn between 350 and 450 million hectares per year. And I was just at a conference in Europe, and they're still wrestling with the numbers because of different satellites getting different numbers and different approaches. But that number is still quite valid, and it's about the size of India. We don't know how many fire starts there are. Most of them are human caused, and the largest area burns are in grasslands and savannas. But it's interesting to note that fire is a necessary component of some ecosystems, like our boreal system. So this is an animation that I see it, but you folks don't see it. So I'm going to use external player so that hopefully you can see it too. And it's really slow. I'm not sure why it is so slow. I'll give it a couple more seconds. I see it moving along on the bottom of the screen, and it's not really absolutely necessary. I can just describe okay, hopefully you see this now after that long wait, and it's just showing how much that pixel burned during a 10-year period, and you can see the decades passing, 81 to 90 there. You can see lots of area burned in South America, Africa, Australia. You can see some of the boreal through Siberia, Western United States, Southeastern United States, as well as Canada. So lots of fire. I'm going to close this now so we can go back to the PowerPoint. So briefly, fire ecology, and this is primarily for the boreal forest. Many stand renewing crown fires. It removes competition, allows sunlight to reach the forest floor, reduces or removes the organic layer, which many conifer species like for regeneration. So your standard climate succession models for vegetation don't really apply much to the boreal. What you see is what you get. Various strategies to deal with semi-regular, high-intensity fires. Some species have serotinous cones sealed with a waxy resin, and needs heat to open it, and fire is often the heat source to open these cones. Jack pine, lodgepole pine, and black spruce has semi-serotinous cones. Suckering, aspen uses suckering, and sprouting, birch, thick bark. Some of the pines, the white pines, and the red pines have thick bark. They can survive strong surface fires, but not the crown fires. So Canada, we have data back to about 1918, 1919 for the country, though there's a lot of guesswork involved in that. So, we're pretty confident from 1970 to present day, the age of satellites, so that we can see what's going on. Currently, we burn there's about 7,000 fires burned, 2.5 million hectares a year. And this used to be about 1 million hectares a year in the early 70s. If you do a running 10-year total, you can see it's a little higher in the graph shown on the bottom left there. burned has doubled at least during this period. And during this period, fire management agencies have become more efficient and more territory is covered by fire management agencies. Despite that, our area burn has doubled, and I and a number of others believe this is due to human-caused climate change. Primarily ground fires, but it's really a mosaic. There are times when it's just surface fires, but the large runs are often ground fires. Highly episodic from year to year, and I believe this is due to primarily to weather. About a third of the fires are started by lightning, but they represent about 85% of the area burned, depending on, this is for all of Canada, and that's for a recent period, but regionally it does vary a fair bit. It can be 50-50 or close to that in many regions. It's all about the extremes in the fire business. The tail wags the dog. So 3% of the fires are larger than 200 hectares. A hectare is about the size of a soccer pitch or a football field, just a little bit bigger than that. But these large fires represent 97% of the area burned. Western United States, 1% of the fire are responsible for 99% of the area burned. So the tail wags the dog. It's all about extreme, hot, dry, windy weather. So this is a map. This work was done by Jen Beverly and Pete Bothwell, and it shows evacuations and structural loss. And you can see that, despite the fires in BC this year and Fort McMurray last year, that fire is an issue, a problem from sea to sea to sea pretty well in Canada. And you can see in the next slide that this is work done by Lynn Johnston, and she's with the Canadian Forest Service and did a master's degree with me a couple of years ago. She looked at the traditional wildland urban interface, and then something we call the wildland industrial interface, or WII, and then there's infrastructure interface. And you can see in the southern parts of Canada, southern parts of the boreal, and kind of with fingers spreading to the north, there's a lot of development on the landscape. So, and this is changing with time and spreading farther north. So lots of development, lots of values on the landscape. So fire management agencies in Canada, among the best in the world. They use the Canadian Forest Fire Danger Rating System for their decision making. The philosophy is for unwanted fire, initial attack. Okay, you hit it hard, you hit it fast, and if it's the size of my office, which is that large, it's easy for a crew to put that fire out. Once it gets to the size of a football field or a hectare, and it's hot, dry, and windy, and the fuels are dry, and especially the conifer, you have a problem. So historically, it's been Smoky the Bear message, and there's kind of two messages. One is you can prevent forest fires, which is a good message. The other is that fire is bad, and that's not the case at all. If anything, fire is natural for many of our forests in Canada and can be seen as beneficial. So some agencies have moved to something they call monitor and manage or appropriate response, and I liken it to the emergency room at your local hospital. And instead of patients arriving, fires arrive. And a fire is 10 kilometers from Prince Albert or a couple kilometers from Prince Albert. It takes half a second to say this is an unwanted fire. You hit it hard, you hit it fast, full initial attack, full suppression. If the fire's 100 kilometers from anywhere, then you say, well, let's see what the values are in the landscape. Let's see what the weather forecast is for the next 5, 10, 15 days. Run a fire growth model for the next 5, 10, 15 days. Where is that fire going to spread? And if it doesn't look like it's going to be a problem, then you say, well, we'll continue to monitor it. And then the next day you get a new fire weather forecast, you run a new fire growth model and do the same thing again. And this allows fire back on the landscape because, as long as we have fuels, ignition, and weather, we're going to have fire. So we have to learn to live or coexist with fire. So Here's maps showing area burnt by fire by decade, and you can see once again it's almost, it's hard to see my mouse here, but it's almost from sea to sea to sea again with this swath of boreal. There is kind of a break or less fire in eastern Ontario and western or southwestern Quebec here. This may be due to climate reasons, but as you can see, lots of fire on the landscape. So we currently spend about $800 million this year, probably exceeded $1 billion, and that's happened before. And these costs are going up. And these are direct costs of fire management expenditures. Of course, protecting Canadians is a priority. There's also evacuations due to fire at the doorstep as well as smoke. And there are issues with northern communities because some have no roads or only one road. And if the fire threatens the evacuation route, then you have to fly people out. So there's lots of consideration for our northern communities. Fire, you have to balance the positive and the negative aspects of fire in making the decision whether to suppress it. Traditional approaches may be reaching their limit of economic and physical effectiveness. Fire management agencies are very adaptive, so they may yet adapt, but if we continue to see more fire, costs will go up. There's no choice. Fire impacts, it's really, about impacts. And it's like real estate, location, location, location. And there's some examples on the slide of fires all over the world. Recent events in 2017, we saw fires in New Zealand, record-breaking fires in Chile, deadly fires in Portugal, South Africa, United States, Canada, BC. And I should mention Saskatchewan and Manitoba had a number of evacuations as well. Smoke-related fatalities globally estimated at over 330,000 per year, and this is mostly due to haze in Southeast Asia. So this is how I look at fire on the landscape. You need the first three are the ingredients necessary, and whether there's people or not, they're operating. So there was fire before there was people on the landscape. But people are on the landscape, so they do influence things. Fuel, what type of fuel, how much fuel, how is it structured, are there understory shrubs to help carry the fire from the surface into the crowns? That's the name crown fire because the crowns of the trees are engaged or inflamed. Ignition, human and lightning, weather, temperature, precipitation, atmospheric moisture. There's also a role for the upper atmosphere, what we call blocking ridges, solar radiation, and of course people. We manage fire. We convert land to agricultural purposes, also cities and highways, railways, etc., etc. So these are all playing into governing how much fire we see on landscape over a period of time. Now, I'm biased. I think weather is the most important factor, hot, dry, windy, and there's a couple reasons why I think that. It's the most dynamic of the three. Also, lightning is a function of the weather, and fuel moisture is also a function of the weather. And fuel moisture is really critical in the fire business because it determines whether a fire will start and whether it will spread. So, this is the reasoning behind why I think fire is the driver. So, our climate has been changing. I'm not going to go into a lot of depth about greenhouse gases. One of the primary ones is carbon dioxide. It's been monitored, observed, if you like, since the late 50s in Mauna Loa, which is on the Big Island in Hawaii. And you can see it's going up, and it's over 400 parts per million, and pre-industrial is about 270 to 280 parts per million. So it's going up, and there's been some bumps and things in it, but it's continues to go up. And as long as it goes up, it will contribute the greenhouse warming potential. So, and you can see there's annual variation, and that's because Hawaii's in the northern hemisphere, and our summer vegetation absorbs carbon dioxide, and much less so in winter. So you get this annual trend. So we're continuing to warm. Now here's another animation. This one worked earlier, and this is the reconstruction of global temperatures. You can see the year in the bottom center, and you can see warm areas, cool areas, until about the late 70s, and then you start to see globally a lot more warming, especially in the northern latitudes, Russia, Canada, Alaska, but even other parts of the globe. So it's a much warmer world than it used to be. And these are observations, reconstructions, and this is from that was from NOAA in the United States. So this is looking at global temperatures, reconstruction back to the 1880s, and you can see that it's been up, it's been down, but then starting in the late 70s, especially if you average it, it's been going up and up and up, and more recently, very much up and up and up. So we are warming, and this is from the Goddard Institute for Space Studies in the United States. But there are other ones from the UK and other American ones that show pretty well the same sort of thing. We are warming. So here's just the year 2015 in the top left, and it shows blues are colder than normal, reds are warmer than normal, and the bright red are record-breaking warm. And you can see that much of the Earth was above normal, and in some cases record-breaking normal. And here's the anomalies. It's just a similar graph to what I showed earlier, except for it's a bar graph. You can see, the warmest years have been the recent years, and the trend is going towards warmer and warmer and warmer. 2016 followed the same trend as 2015. So global warming doesn't mean that every year it's going to be warmer everywhere. You can see there are parts of the North Atlantic that were below normal, parts of the Pacific and the Southern Ocean, and in this one there wasn't enough data, so it's white, which they don't have any information on it. But once again, much of the globe was above normal. So here's December 2016, and you can see there are some very significant departures. The scale on the bottom shows these are degrees Celsius, over 7 degrees Celsius above normal from the typical baseline, which is 30-year average, which was 51 to 80 in this case. So very much above normal for most of the globe, and this shows it by latitude. And you can see the high latitudes are around very high latitudes in the northern hemisphere, around 7 degrees warmer than normal. So during this past winter, there were a number of events where there was some very warm air in the Arctic, even getting above zero at the North Pole in the middle of winter, and the departures were ranging in the 30 degrees Celsius above normal, and this happened on 3 or 4 occasions during the winter. So very warm air, relatively speaking, was making it up into the Arctic, and first time we've seen that kind of departures at those high latitudes. So we use something called global climate models, global circulation models, to project what the weather will be like in the future. And it looks like it could be up to 6 degrees warming by the end of the century, according to these models. Greatest increases at high latitudes over land in winter and spring, except for the Arctic Ocean. And once the Arctic Ocean becomes seasonally ice-free, there will be some very large departures. Of note and interest to fire is the predicted increases in extreme weather: heat waves, droughts, floods, fire, windstorms, ice storms. There's a lot of spatial and temporal variability in climate change, and these Increases in extreme, we've seen recent publications on the jet stream, and that the changes in our jet stream, and I'll talk a bit more about this later, has led to more extreme weather. And more extremes often means more fire. So this is work from 2004 by Nathan Gillette and others. It looked at area burned in Canada and observed temperatures, and then simulated temperatures due to warming from human-caused warming alone. And in that paper, we say that it is likely that human-caused warming is responsible for the increase in area burned. And here's another animation. Now, instead of what was observed, this is just one model showing what the future may be like. And once again, you see the year in the top center here, 2040s going through. Reds are warmer than normal, blues are colder than normal. You see that there are areas in the Southern Ocean off Labrador that have no warming or even cooling, but much of the globe is much warmer than present day, which is much warmer than we used to be middle of the last century. So this warming is supposed to continue, and I see no reason to doubt it. There will be regional variability and year-to-year variability. But overall, globally, we are warmer and will continue to warm. So this is also work from about 10 years ago looking at the Canadian GCM and the Hadley GCM and looking at the past to say what fuel, moisture variables, and weather variables were related to area burn, and then use those relationships in the future. And you see that there's a lot more fire in the future. They suggest doubling. Work a few years later looking at Alaska and northwestern Canada, suggested increases up to 5.5 times current levels, which is a significant increase. And here's some work done by Shangli Wang and others, and it's looking at the median number of spread days, days where the fuel is dry enough and the weather is conducive to spread. And you can see from the baseline 1981 to 2010, and then up through this century, that the number of days where fire can actively spread is increasing significantly, especially in the central boreal. So what a lot of the papers suggested earlier, this paper and this paper and this paper, and that paper, all right, hopefully I'm not going too fast, so Nathan Gillette, and this is Flannigan et al., and this is Bolshe et al., found a relationship between temperature, and there are other papers that have found this relationship with temperature explicitly. The warmer it gets, the more fire we get. And what I'm talking about is over a region, say the size of northern Alberta, over half a month to a month, temperature is key. And why is this? Well, there's three reasons. The warmer it is, the longer the fire season. And in Alberta, our official fire season starts March 1st now. It used to be April 1st. And it's because our fire seasons are starting earlier. Work done by other colleagues, Doug Wolfer and Alicia Green. I should have that reference here. Have shown that in Alberta, our fire seasons are starting earlier. Second, the warmer it is, the more lightning we have. And everything else being equal, the more lightning, the more fire you have. Work done in the United States by ROMPS suggests for every degree of warming, they get about a 12% increase in lightning. I expect it's something similar for Canada, or perhaps even more dramatic because our lightning seasons are probably getting longer. And the last reason, which is probably the most important, is that as the temperature increases, evapotranspiration increases non-linearly. And so this means drier fuels unless there's an increase in precipitation. And work last year suggests for every degree of warming, you need about a 15% increase in precipitation to compensate for the drying effect of warming. And if you trust the GCMs or the models of the future, almost nowhere in Canada are there increases in precipitation to compensate for this drying effect. So the bottom line is that fuels will be drier. Drier fuels means it's easier for fires to start and spread. So there's been a number of papers looking at climate change and fire in Canada and around the world. And many of these, not all, but many suggest increases in area burn and in fire occurrence and in length of the fire season. And fire intensity severity has been more of a mixed model, though there are some recent papers suggesting that these are increasing as well, and especially in Canada. So this recent work published in ERL, Environmental Research Letters, on fire intensity, I'm just going to go over quickly in the last 10 minutes here or so. So we use 3 GCMs, the Canadian, the Hadley, and one from Australia, 3 representative carbon pathways, 2.6, 4.5, 8.5. We calculated the fire weather index system for a baseline, 71 to 2000, and then compared that to future periods. And the FWI system is based on temperature, relative humidity, wind speed, and precipitation. So we calculated the fire intensity, the rate of spread, depth of burn, fuel consumption, crown fraction burn, all using the Canadian Fire Behavior Prediction System. We also calculate days above specified threshold, head fire intensity of 2,000 and 10,000 kilowatts per meter. And these are important because around 2,000, this is when it becomes unsafe to use direct attack by people on the ground. And at 10,000, that's where aerial attack becomes less effective. So we used a fuels database. We started with a 250-meter database that was built by Natural Resources Canada, if memory serves. But we aggregated it to 40 kilometers by 40 kilometers to make the processing go a little quicker. And you can see that, the broad brush, it's not a bad way to tackle the fuels. So what's happening in the future? Well, let's just look at head fire intensity of 2,000 kilowatts. And the RCT is in the towards the upper left, and the time period. So it's rotating through 4.5, which is a moderate scenario, to the more extreme scenario of 8.5, from early in the century to later in the century. And you can see that the number or the percent change in days of head fire intensity is increasing significantly, 400% or more in cases. But it's also important to keep track of the number of days, and we'll look at that in a second. Now we've switched to 10,000 kilowatts per meter. This is where aerial attack becomes less effective. Once again, we're looking at the percent change in the number of days above 10,000 kilowatts. Now you'll see some areas in the Yukon, the Northern Territories, that are completely white, and that's because currently in the baseline climate, they don't have any days above 10,000, according to the models we're using. So, look at the change of days now. So how many actual days are above 2,000, and what's it compared to the baseline? Once again, using the 2 RCP scenarios, 4.5, and the 2 time periods, kind of early century and late century. And you can see in some places for 2,000, it's 40, 60 days more where it's 2,000 or above. So that's a significant increase. At 10,000, once again, the 2 scenarios, the moderate and then more extreme, the 8.5, and early century and later century. And once again, it's a similar sort of thing where we're starting to see days, and we're starting to see some of the days showing up in more extreme scenarios farther north, because we're actually getting days above 10,000 kilowatts per meter. And so there is a significant increase in the number of days above these thresholds. So escape fires, so increased fire intensity will lead to more escape. And looking at extended attack simulations suggests that proportionally there'll be much larger increases. So if you get twice as many high intensity fire escapes, it may lead to 4, 6, or even 8 times more area burn. So, these are key indicators that fire management will be even more challenging in the future. Now, the jet stream. The jet stream is that band of fast-moving air, 10, 12 kilometers, 8, 10, depending on the season and the location. And if you're getting a flight, if the jet stream's with you, you get to your destination earlier. If you're fighting the jet stream, you're delayed. And the thinking here is that with climate change, high latitudes are warming much faster than the equatorial regions, particularly in the northern hemisphere. And this temperature difference gives the strength, the energy to the jet stream. And the high and low pressure systems follow this jet stream. So a few years ago, there was a paper out saying our jet stream is getting weaker. So it's meandering, it's lazy, like a slow-moving river. You get eddies, and where you get the ridges, you get droughts and fire, and when you get troughs, you get rain and flooding. And we've seen a lot of the extremes recently in terms of flooding and drought, different parts of the globe. And if this jet stream continues to weaken, we should expect more jet streams. Fire people have known for decades that blocking ridges, that's a ridge that diverts precipitation-bearing systems to the north or south, sometimes called omega blocks because it looks like the Greek letter omega, as you can perhaps see in the bottom diagram. You can see my mouse here. This one's over Yukon, eastern Alaska. And, so if this ridge parks for 7 to 10 days or longer, it's usually warm and dry, so it dries out all the fuels. If you have ignition and the ridge moves off or breaks down, you get some wind, and away we go. So changing jet stream, more extremes, more fire. So what can we do? So in terms of Canada, in terms of climate change, we expect more extreme weather, more fire. We go back to the 3 natural ingredients, fuels, ignition, and weather. What can we do? We can't do anything about the day-to-day weather. Climate change, yes, we can do something about, but for now, let's say we can't do anything about the fire season weather for 2018. We can't do anything about lightning, but we can do, and we do things with respect to human-caused fires. Perhaps we can do more. We can have more forest closures that work if they're enforced. But that leaves fuel, and there's a program called Fire Smart Canada, has a number of, I believe, 7 principles. Fuel management is one of them. So removing, replacing conifer fuels with something less flammable, so that the intensity would be lower, which would give fire management a chance to put the fire out. The Canadian Forest Fire Danger Rating System is a great system, though it's been around for parts of it, been around for about 40 years. And the demands on fire management has changed a great deal, so it's time to update that. Need for an early warning system, expand appropriate response. So for the fires in BC this year, if BC called Ontario and Quebec and said, we need firefighters, it takes about 3 days from the time of that call before that firefighter, before he or she is on the fire line. So if you had a system to give you an idea of where and when to expect fire, you could move more resources to the appropriate location at the appropriate time. So the weather's changing, but also our landscape's changing. Now more than ever, Canadians live and work in the forest. Development's increasing, and here's a map of Alberta showing population, also investment. And you can see, in the north, near Fort Worth, there's been lots of investment, and even parts of the northwest it's starting to occur. And this is happening in Ontario and other provinces as well. And there's an op-ed from Los Angeles Times. In the States, in the last 10 years, 60% of new homes in the U.S. have been built on lands adjacent to fire-prone public land. I expect it's probably similar to that in Canada as well. So, yeah, can we do things differently? Yes. So I just wanted to show this slide. In Canada, for the last 5 years, we've had over 3 million hectares burned, and nowhere in our record have we had that. The closest that we've come was 79, 1980, and 81. We had 3 years in a row had 3 million hectares. So are we changing this the new normal? Perhaps. Here's BC. So 1958 had been the previous record, and was 800-some-thousand hectares burned. It was kind of head and shoulders above everyone else. Previous to this year, 1961 was in second place with 400-some-thousand hectares. And I haven't looked recently, but we're probably getting close to 1.2 million hectares. So it's kind of head and shoulders above what was head and shoulders above everything else. So a very active year in BC. So I'm going to wrap up. Fire and weather are strongly linked. Changes in forest fires may be the greatest early impact of climate change on forests. The forest pest people might argue mountain pine beetle and other pests, and they may have an argument. Fire activity will increase in a changing climate, warmer climate, but will be variable in time and space. Significant increases in fire intensity are expected, and these increases will mean that fire management will be very challenging in the future. And here's a Twitter account, and as Annette mentioned, I'm with the Canadian Partnership for Wildland Fire Science. It's a 3-way partnership, but we're looking to expand. So hopefully we can move from there, and we can go to the questions now.
Perfect.
Thank you.
Yeah, great. Thanks, Mike. So we have about 15 minutes or so left for questions, and so we already have some in the chat box, Mike. So if you scroll up, the first one's from Rebecca Hennings. So on page 6 of the PowerPoint, if big fires make up 97% and lightning fires 85%, does this mean that big fires are mainly due to lightning?
Yes. Okay. Not that human-caused fires aren't important, because if you remember, it's all about impact. So the Fort McMurray fire was human-caused, and that had significant impact. Many of the lightning fires occur in remote areas away from people. They often occur in clusters. It takes longer to detect, longer for fire management personnel to get there if they wish to suppress that fire. So yes, a lot of the large fires are lightning fires, but a lot of the impactful fires are people-caused fires. Slave Lake was also a person-caused fire, but in terms of area burn, yes, you're correct.
Perfect. So the next one here is from Ashley North. So is the mapped data shown on slide 8 publicly available?
Slide 8. Okay, so I changed the screen there, but yes, it is. It depends what resolution you want. Beaulieu at the Canadian Forest Service. Lynn Johnston is on maternity leave right now, otherwise I would direct you to Lynn. But Beaulieu I'll give you his email address, bo.lu@canada.ca is the person to contact if you wish to get the data layers.
Perfect. Fantastic. So another question here from Rebecca Henning. So the burned area has doubled. Has the frequency, or rather the intensity of the fires changed, maybe due to climate change? Is there a natural variability of fire intensity over the last centuries that could also explain the current increase of fire occurrence? And she's especially interested in Eastern Canada and James Bay. Projections there say that there's going to be more precipitation, and so will this be able to compensate for the projected increase in wildfires?
So, yes, and some of the recent work done by Mike Watton and others first paper talks explicitly about fire intensity increasing pretty well all across Canada, and depending on what scenario you use in the future. Has it changed from the past? That hasn't been studied, but I don't see any reason why it can't be studied. My guess is as we get warmer, probably intensity has increased. It's not as simple because it's a kind of multi-step calculation, because it depends on the fuel and the weather in combination to get the intensity. So if you have conifer fuels, especially if there's an understory or ladder fuels that carries fire from the surface into the crown fires are high intensity. Okay, so conifer fuels are a red flag. If you have conifer fuels near a community or your cottage or wherever you are, this is when fuel management needs to happen, and you've got to reduce the number of conifers so it's harder for it to carry a crown fire, or you remove the conifers and plant deciduous or grass, green grass, or use sprinklers. So yes, but the warmer it gets, the more hot, dry, windy we have. If the fuels are unchanged, the higher the intensity will be, and the more difficult it will be to manage that fire. The more likely there will be fire escapes and large fires.
Perfect. Thanks, Mike. The next question here is from Don Griffin. So with the increase of fire events, is the appropriate response model that is not as focused on initial attack the right way to go?
So I think appropriate response is the right way to go, but I don't want to get the impression that there's not this focus on initial attack. Initial attack is key to success, but initial attack on unwanted fires. So those fires that are close to something of value to society, whether it's a community or a watershed, what have you. If your agency has determined this is a priority area that we cannot allow fire, then you still want to have that initial attack capacity to put out, to hit it hard, hit it fast. So initial attack is probably more important than ever, but the determination of what's allowable fire versus what's an unwanted fire is key, and it has to be made in a very timely fashion, because time's of the essence, because you have to get under extreme conditions. We're talking about minutes that you have a window to put that fire out, and after that you could be waiting till the weather changes or the fuel changes. So you want initial attack on those fires that are unwanted.
Perfect. Thanks, Mike. So from Fred here, what is known about the chemistry of the aerosols in the smoke plumes and its impact on downwind water resources?
Well, this is a question outside my area of expertise, especially with relation to the impact on water. What I do know is that there's a lot of material in the emissions in the column, and at times through something called pyrocumulonimbus, it can be injected into the stratosphere, and it can circle the globe multiple times, and this is a particular concern from a climate change perspective in northern hemisphere spring, where we get fires and pyrogenic carbon soot gets deposited on snow or ice and in the Arctic or Greenland, and changes the albedo, the reflectivity. So a white surface reflects most of the solar radiation back into space. A black surface absorbs the heat and accelerates melting. So there's a website called darkice.org that's looked at this, and it's suggesting that it's accelerating the melting of glaciers in Greenland because of soot from forest fires or wildland fires being deposited on.
Perfect. And I think you just answered Pal's question right below it um, about the extent of how soot from fires will affect the albedo.
Yes. Yeah.
So from W. Smith, so what is the overall implications of increased fires in Canada for the carbon cycle and the carbon budget?
Okay, that's a good question. And right, there's been some estimates of how much emissions there are from forest fires, and it's not a huge amount, but our current system does not handle peat fires very well. It really was developed for upland forests versus wetland forests, peat bogs, fen, things like that. So we might be underestimating, and we're just doing right now on emissions from fire for the future suggest that we may be increasing a great deal. I think the key part here is that there's potential for more emission, and especially from peatlands or permafrost, where there's other hydrates that are currently locked in a frozen state, but if permafrost thaws, these can be released, and these could be significant amounts. I often cite Susan Page work in Indonesia, and in one year, particularly bad year, estimates of emissions from peat fires were equivalent to 20 to 40% of global fossil fuel emission. We have 30 times more peat in Canada, Alaska, and Siberia than there is in Indonesia. Different burning conditions, granted, but there is a potential for significant increases, especially with more drought, which allows the wetlands to dry out and deeper burning. Already, this past year, we see things that burn quite deeply, talking meters in Alberta and other places, and this could possibly be part of a positive feedback. That is, I've argued that the warmer we get, the more fires we have. The more fires we have, the more greenhouse gas emissions we have, which makes it warmer, which promotes fire. And given that, I am going to show a video that's not part of wrap. Sorry. I'm still intending to show a video. I'm just trying to find the video. Here we go. And this was full screen here. Shot with a cell phone. And this is a peat fire in northern Alberta. It's August, if I recall. And they're doing what's called mop-up, when you have to dig things out and put water on and get the fire out. So the firefighter is throwing some peat, smoldering peat up in the air, and mixing with the oxygen, it bursts into flame like spontaneous combustion. It's like sawdust. And so I've never seen anything like that before. So shows you that there's always things to learn. So that's peat burning there. So yeah, potential for positive feedback and more greenhouse gas emission in the future.
Very interesting. Thanks, Mike. Great. So the next question here is from Emily Gray. So could you talk a bit about how development in areas vulnerable to fires could be made less vulnerable? So for example, like buffers.
Sure. Well, there's a couple of things. Building codes, and some of it's pretty logical. Don't have wood shingles on your roof, don't have flammable material right adjacent to the walls of your structure. And the thing about that is that you can do everything right, but your neighbors on either side can do everything wrong, and if their house catches on fire, the likelihood of your house catching on fire increases greatly. So it really needs to be a community thing. And then there is the fuels around the community, and using things like sprinklers are an excellent idea. Though you have to be careful that you have a water supply and an energy supply when a fire comes into town, because we've seen in recent examples where power and water pressure is lost due to a fire coming into town. So you have to have an independent system almost to run. And then, removing the conifers. Now the trick becomes that many of the homes lost are due to burning embers. So bits of burning material, twigs, needles, leaves, what have you. And during extreme conditions, these embers can spread as much as 2 kilometers in advance of the head of the fire. And that happened in Slave Lake in 2011, where there were spot fires in the town of Slave Lake, while the head of the fire was still 2 kilometers from town. So that becomes a large area if you have to take everything down 2 kilometers. Now that's the extreme side of things. But you want to remove conifers or thin the conifers, prune the conifers, so that the distance between the surface of the forest floor and the bottom layer of branches is large. So it's hard for it to spread up into the crown. Or you thin it so much that it won't support a crown fire under normal conditions. I mean, it's important to realize that we can reduce the risk of fire, but we can never eliminate it. As long as there's fuels, ignition, and weather, we're going to have fire. I've often proposed having golf courses, baseball diamonds, soccer pitches kind of encircling a community, or on the side that's most vulnerable to fire, to have that buffer zone. Green grass doesn't burn, okay? So you have areas with grass or no trees, you can't get a crown fire, and this helps protect the community. I would recommend people visit the Fire Smart Canada website, because fuel management is just one of a number of aspects. It's probably the most obvious one and the one that's cited the most often, but there's a number of principles, I believe 7 comes to mind, that are involved in fire smartening a community.
Perfect, thanks Mike. So there's 2 more questions in the chat box, and then I do want to see if anybody has questions on the line, and then we'll wrap up. So the next ones are from Clara Bartha, who's unable to log in, but she's listening over the phone. So how can reforestation efforts help to expedite the regrowth, and how can we geographically be strategic in doing that? And what does this loss in forests mean to ambient atmospheric conditions and oxygen availability to humans and their ability to absorb pollutants globally?
Okay, there's a lot of questions there. So, the boreal forest has survived and even thrived for thousands of years in this environment. Are we exceeding things that we've seen in the past? Some regions definitely not. Some regions we may be approaching exceeding, perhaps in a place or two. So the forest is really good at regenerating under normal circumstances. I have a PhD student now looking at what we call double whammies, where you get fire after fire in close succession, or insects and then fire, or harvesting and then fire, and how resilient is it to these kind of double whammies, given with changing climate. And so that's under investigation right now. So I can't give you an answer yet, but hopefully we'll have one soon. If fire becomes too frequent, the trees will disappear. Okay, but what are you left with? Shrubs, grass, and grass can burn almost every year. Shrubs, depending on what type of shrubs, can also be very fire prone. So vegetation won't disappear, but in places over time, our forests may disappear. Now, some people argue planting strategies where you need it. I mean, most often use natural regen where possible, but where you have to plant. A lot of people are proposing using deciduous trees because they will suppress, especially the high intensity fires, but even suggesting there'll be less fire if we have a more deciduous dominated landscape. And so that's a consideration, and over time that could work, but there's market forces at play here, of course, because if you don't have a market for that much area covered by deciduous species, what can you do? So yeah, I'm not sure if I answered all your questions, but there will continue to be vegetation in the landscape, and some of these ideas about planting deciduous, they have limitations, not just market forces, but about 20% of our forest is what we call wetlands or lowland forest, and deciduous won't do well in a peat bog or a fan, where only a few conifers will survive.
All right, great. Okay, and then one last question here in the chat box from Rebecca. Do the very big fires, so the 97% burned area, occur in one region specifically, or more western or eastern Canada, or in more isolated areas because they can't be controlled as easily?
So actually, I haven't done that analysis at that local scale. There will be regional variability, of course, where fires are allowed to burn freely. It will be. I actually have to do the analysis to answer that question. But you get escape fires, almost anywhere there's a forest. I mean, so the grasslands or the agriculture areas of southern Alberta, Saskatchewan, Manitoba, you can get grass fires and things like that. Southern Ontario, it's not going to burn. A large fire anyway. So you need a continuous forest. I think I'll stop rambling there. Okay. Sorry.
Great. No worries. Okay, we are a little bit over time, but I just want to give, if anybody has a burning question, sorry for the pun, but over the phone, just hit *6 and that will unmute your line. Are there any questions over the conference call line? More seconds. If not, I think your email is on the last slide there, Mike. Is it okay if anybody has any other questions that they can email you?
Yeah, just email me. I'll try and answer any questions that come up.
Perfect. All right, so I guess we'll wrap up for today. So thanks again, everybody, for joining us. We hope you enjoyed it, and a very, very big thank you to Mike for your time and effort, for a great presentation. Any last comments from you before we sign off here?
No, it's fun. These webinars are hard because you can't see the audience and you can't even hear the audience until the end, and so it's a bit more challenging than a regular seminar or talk. But I'm thankful for all the questions, and awesome. My pleasure.
Perfect. Well, yeah, again, thanks for joining us today. So that's it for us. I guess we'll sign off. So everybody have a great day and catch you next time. Thanks, Mike.